Hello my dear students, welcome back to the discussion on solved problems in fluid statics. I am your SumamMiss. My channel name is also SumamMiss. You can watch my videos on my channel. Today we are going to discuss about the problems related to hydrostatic force acting on inclined, vertical and hollow plane surfaces. These are typical problems commonly expected from this portion. We have learned previously that when a plate is exposed to a liquid, such as gate wall in a dam, the wall of a liquid storage tank, or the hull of a ship at rest is subjected to fluid pressure distributed over its surface. When the surface is plane, the forces due to fluid pressure acts on the small element of this plane will be parallel and normal to the surface. So resultant hydrostatic force can be calculated by summing up all these forces. In most of the cases, other side of this wall is exposed to atmospheric pressure. So atmospheric pressure is acting on both sides of the wall. So that can be cancelled. So we can work with gauge pressure only. From this figure, you can see that intensity of the pressure that varies and it increases when we move down. That is just because the pressure at any point in static mass of fluid depends upon its position with respect to the free surface and specific weight of fluid. So the intensity of pressure here equal to P equal to rho gh, where h is the depth of water that is available in this tank. The resultant hydrostatic pressure that is acting through a point that is called center of pressure. So since pressure varies when we move down from top to bottom and it increases when we move down, the resultant hydrostatic force that is acting at the point that is called center of pressure, which is well below the center of gravity of this contact surface. Now let us discuss the problem related to hydrostatic force acting on the plane surface. So in this problem, a culvert draws of water from a reservoir, the side of which are inclined at 10 degree to the vertical. So this is the reservoir. So this side is inclined at 10 degree to the vertical. The entrance of the culvert is closed by a circular gate. AB represents a circular gate, the diameter of which is given as 1.25 meter, which can be rotated about its horizontal diameter. So we have to prove that the turning moment on the gate is independent of the depth of water if the gate is completely immersed. So this is the immersed condition of this gate. G, that is the centroid of this circular gate, which is at a distance of h bar from the free surface. Total pressure P, that is acting at the center of pressure, which is below the center of gravity of this gate, and it is at a distance of hp from the free surface. Since this wall of the reservoir is inclined at an angle 10 degree to the vertical, this theta that is equal to 80 degree. So total pressure acting on this plate that is equal to rho g into A into h bar. Rho g represents specific weight of water, A that is area of this plate, and h bar is the position of center of gravity of this plate with respect to the free surface. The center of pressure can be calculated as hp equal to h bar plus ig sine square theta divided by h bar. Ig represents the moment of inertia of the circular gate. So the calculation of the total pressure and the center of pressure is well discussed in this video. So if you want more details, you can refer this. Now we have to prove that turning moment on the gate is independent of the depth of water if the gate is completely immersed. So how will you calculate the turning moment? So turning moment equal to this resultant hydrostatic force multiplied with Gc. So how will you find out Gc? So Gc equal to Co minus Go. So how will you calculate Co? C is the position of the center of pressure, which is at a distance of hp from the free surface, and theta equal to 80 degree. So Co that is equal to hp by sine theta. So what is hp? hp is the center of pressure, that is equal to h bar plus ig sine square theta by ah bar. So if you are substituting for hp, distance CO can be written as h bar by sine theta plus ig sine theta by ah bar. Similarly, the position of G is at a distance of h bar from the free surface. So GO that is equal to h bar divided by sine theta. So our idea is to calculate GC, which is equal to CO minus GO that is equal to, so this is CO and this is GO. So this term is common, so that will get cancelled. So the distance GC, that is equal to Ig sin theta by H bar. So next step is to calculate the moment of total pressure P about the horizontal diameter, that is equal to P into GC, that is equal to P, that is the resultant hydrostatic pressure or total pressure P, equal to rho G into H bar multiplied with GC. So H bar will get cancelled. So final expression is rho G into Ig sin theta, which is independent of depth of water. So this expression can be utilized to find out the turning moment in this condition. Next step is to calculate the value of this turning moment. So theta, that is equal to 80 degree, Ig, that is the moment of inertia of this circular plate, that is equal to pi d raised to 4 by 64. So diameter of the circular plate is given to you. So turning moment M equal to rho G into Ig into sin theta. Rho means density of water, that is 1000 into 9.81 into Ig, that is pi d raised to 4 by 64 into sin theta. So if you are substituting the corresponding values, turning moment is calculated as 1.1578 kilonewton meter. This concept is very much useful to make a decision regarding drawing of the water from a reservoir. Next problem is regarding the calculation of hydrostatic pressure force on one side of the plate and the depth of central pressure. So plane is a hollow equilateral triangular plate, and this hollow triangle is immersed under water with the base upwards and vertex downward, and base is parallel to the free surface, and the base is at a distance of 1 meter from the free surface. So we have to determine the hydrostatic pressure force on one side of the plate and the depth of central pressure. H bar is the combined center of gravity of this hollow equilateral triangular plate, and HP represents the center of pressure. So theoretical details of the calculation of total hydrostatic pressure and depth of center pressure is given in this video, so you can refer this. So the expression for the total hydrostatic pressure equal to rho G into A into H bar. Rho G is specific weight of water, A is the triangular area, H bar is the distance of the center of gravity with respect to the free water surface. For equilateral triangle, the expression for area, that is equal to root 3 by 4 A square. A is one of the side. So area of the triangular portion equal to root 3 by 4 into 4 square minus root 3 by 4 into 2 square, that is equal to 5.196 meter square. Next part is we have to calculate H bar. So in the present problem, the surface is a hollow equilateral triangular plate. If the triangle is not equilateral, then we have to use this general expression as X bar equal to, X bar means the position of center of gravity of this hollow plane with respect to the base, which is calculated as A1 H1 bar minus A2 H2 bar divided by A1 minus A2, where A1 is area of PQR and A2 is area of ABC. H1 bar is the distance of the center of gravity of PQR with respect to PQ. Similarly, H2 bar, that is the distance of center of gravity of the triangle ABC with respect to the base PQ. So in the present case, the surface is hollow equilateral triangular plate. So in that case, the position of center of gravity for both triangles are same. But if you are using this formula, then we have to calculate the area of PQR and area of ABC and H1 bar and H2 bar. So H1 bar is the distance of the center of gravity of PQR with respect to the base. Similarly, H2 bar is the distance of the center of gravity of the triangle ABC with respect to the base PQ. So that means this distance plus distance from AB to the center of gravity of this triangle. So X bar can be calculated as X bar equal to area PQR into H1 bar minus area ABC into H2 bar divided by area PQR minus area ABC, or X bar equal to 1.154 meter. Remember, in the present case, the surface is hollow equilateral triangular plate. So center of gravity of the both triangle is same with respect to PQ. But in this case, it may be different. So our idea is to calculate H bar. H bar is the distance of the center of gravity of this hollow equilateral triangular plate with respect to the free water surface, that is 1 plus X bar. So h bar equal to 1 plus x bar, that is equal to 2.154 meter. So h bar is calculated. So next step we can calculate the total pressure, that is equal to rho g into A into h bar. So if you are substituting the corresponding values, then the total pressure equal to 109.831 kilonewton. So next step is to calculate the center of pressure. So the expression is HP equal to h bar plus Ig divided by AH bar. H bar we already calculated, A that is also known, then Ig that is moment of inertia of this hollow equilateral triangular plate. So moment of inertia of the triangle, that is equal to B into h cube by 36, where B is the base and h is the distance from the vertex to the base. Since it is a hollow equilateral triangular plate, Ig equal to moment of inertia of this outer triangle minus moment of inertia of this inner triangle. That is 4 into h cube by 36 minus 2 into h cube by 36. The values in red color represents the altitude of this outer triangle, whereas this represents the altitude of this inner triangle. So if you are substituting, then HP equal to 2.54 meter. So while doing the problem, you have to always remember the equations for the moment of inertia of different shape of plane surfaces. Next problem is also the calculation of total pressure on one face of the plate and position of center pressure. So this is circular plate which is immersed underwater. So upper edge is at a distance of 1 meter from the free surface, whereas lower edge is at the distance of 4 meter from the free surface. So diameter of the circular plate is given as 3 meter. So details of total pressure and center pressure is given in this video. The expression for total pressure equal to rho g into A into h bar. So it is a circular plate. So area of the plate equal to pi by 4d square, and h bar equal to distance to center of gravity with respect to the free surface. So that is equal to 1 plus diameter by 2, that is equal to 2.5 meter. So the total pressure force equal to P equal to rho g into A into h bar, that is equal to rho g into area into h bar. It is equal to 173.357 kilonewton. So position of the center of pressure, that is equal to h bar plus Ig by h bar. So that is equal to, so Ig, that is moment of inertia of the circular plate, is calculated as pi d raised to 4 by 64, that is equal to 3.976 meter raised to 4. So when you are substituting these values, HP equal to 2.725 meter. Now the session comes to an end. Today we have discussed 3 typical problems regarding hydrostatic force on plane surfaces, which are commonly expected from fluid statics. For the time being it is enough. Thank you. Awaiting your comments. For any clarification you can